into the world of reinforcement learning, a paradigm that learns how to make optimal decisions through interaction with an environment. Understand the key concepts of agent, environment, state, action, reward, policy, value, function. Explore the intricacies of RL policies and get introduced to Q-learning, a model-free RL algorithm for learning optimal policies. Learn about Q-function, Q-learning update rules, and strategies like Epsilon Greedy for balancing exploration and exploitation. Venture into the realm of deep reinforcement learning, where deep learning meets RL to handle complex tasks and continuous state action spaces. Discover how deep networks can be used learning policies directly and the challenges faced in this domain. Finally, see RL in action as we delve into the applications in control problems, from robotic control to autonomous vehicles and industrial processes. Learn how RL can improve control system by learning adaptive and optimal strategies. Welcome to our introduction to reinforcement learning, where agents learn by trial and error, navigating the exploration versus exploitation trade-off to achieve long-term cumulative rewards. Central to reinforcement learning are concepts like the agent, environment, state, action, reward, policy, value function, and Q function. Today we will delve into reinforcement learning policies, including Q-learning and model-free algorithm for learning optimal strategies, and explore how deep reinforcement learning combines reinforcement learning with deep learning to tackle complex tasks in various domains. Finally, we will discuss the application of reinforcement learning in control problems, showcasing its real-world impact in optimizing systems such as robotics, autonomous vehicles, and industrial processes. Let's dive in. Reinforcement learning is a powerful type of machine learning inspired by the principle of trial and error. It's used in various applications like gaming, control, prediction, and decision making. In RL, an agent learns from its environment by interacting with it and receiving reward or punishments. This learning can be model-free, where the agent learns a policy or value function directly from its interactions, or model-based, where the agent first learns a model of the environment and then uses it to plan actions. A key aspect of RL is the reward system, which guides the agents towards beneficial actions. Just like a dog learns how to obey commands for a treat, an RL agent learns to take the right actions for a reward. However, designing a good reward system can be a complex task, as it varies for each application. Reinforcement learning policies are crucial in predicting rewards at each step and planning actions to minimize the chance of receiving a low or negative reward. They operate independently from the reward system, but their mechanisms should be in synchronization. Reinforcement learning policies are standardized to have specific applications, including action and state space, and off or on policy reward prediction. Q-learning, one of the most used policies, is based on the Bellman equation and helps predict reward at each time step. If the prediction is incorrect, the policy needs to be improved, aiming to minimize the difference between the predicted and actual reward. Deep reinforcement learning combines the power of deep learning and reinforcement learning. We use deep learning techniques to approximate the Q function in reinforcement learning, adjusting the weights of our artificial neural networks through reinforcement learning methods. This approach eliminates the need to store the entire Q function at every step, and thus reduces memory requirements, making it particularly effective in dealing with high-dimensional state spaces. Reinforcement learning is a powerful tool in control problems. It serves as a trainer for control algorithms, especially in tasks involving low-dimensional and continuous time processes. A prime example of this is deep deterministic policy gradient algorithm. In this setup, the error signal is treated as a state, while the control of the plant is seen as the action. To achieve optimal controller performance, reinforcement learning employs a reward system that emphasizes the stability of measured error. Rewards are given when this error is small, and punishments are applied when the error magnitude is significant. Reinforcement learning is adaptable, learning from experience to improve over time. It operates autonomously once trained, ideal for applications like autonomous vehicles and robotics. Reinforcement learning can handle complex environments and aims to maximize rewards, leading to optimal policies. It can also generalize knowledge across similar states, performing well in diverse environments. This makes RL a versatile tool for various applications. And let's continue with benefits that reinforcement learning can bring to us. This tool that allows us for exploration and discovery of optimal strategies. It can lead to cost savings in industries like finance and supply chain management through improved decision making. RL systems continuously learn and adapt, optimizing processes for efficiency and performance. The techniques are versatile, applicable across domains, and can be used to develop systems that collaborate with humans, enhancing decision support in various tasks. At the end of each unit, you will find several questions to test your knowledge. Here's one of the questions. Which natural principle was reinforcement learning inspired by? The answer lies within the materials covered in this unit.